Board on this computer. All right. Okay. So in welcome to CE 321, we're talking about sight distance issue. And again, this is your reading assignment 7.2. As we have mentioned before in the class that you should be reading all these assignments. Now, sight distance as a term, it's a simple term. It means exactly what it says, right? Sight distance. Sight distance means the length of the road surface which a particular driver can see with an acceptable level of clarity. Now, on all roadways at all times, we need to provide a certain sight distance for the drivers to be able to complete certain maneuvers. The least of them is the stopping sight distance, okay? So sight distance is how much you can see, and then stopping sight distance is how much do you need to stop before hitting a hazard at that distance, right? So obviously, if you have a straight road with no curves, no visual obstruction, you will be able to see a larger distance. Now here in roadway design, we don't necessarily talk about the issue of fog, for example, or some other temporary obstruction visibility, right? So we are usually, during rain, for example, or some kind of a snowstorm or fog, you might have temporary sort of limitation on your sight distance. And we don't exactly talk about that, although those could become important and you might want to provide certain warning signs. And that's why sometimes you can get a ticket, even if you're going speed limit, and that might say that unsafe speed for conditions or some other violation like that, because then, or reckless driving, whatever the cop decides to do at that point. But the idea is that you might have to slow down. But in the roadway design class, in this portion of the class, all we are talking about is in clear weather condition, the typical conditions that you will observe on the roadway, how much roadway are you able to see free of any physical obstruction? A permanent physical obstruction is all we are talking about. Okay, so just kind of keep that in your mind, is that as we are solving these problems, we're not talking about special cases, temporary cases that arise due to weather or whatever. We are talking about permanent physical obstructions that would cause somebody to not be able to see, far enough distance on the road. Okay, and we want to make sure that people can see that. Now, stopping is the primary maneuver that you have to always be able to do if you spot an hazard on the road. And that's why it's an absolute requirement for roadway design to have stopping sight distance. The distance you need to stop, that much distance should always be visible to the driver. Now, think about, how do we estimate stopping sight distance? So we'll talk about that next. Is that so before I get to that slide, let me ask you this, right? How much distance do we need to stop? What does that depend on? Well, speed, right? If you're going faster, you will need more distance to stop. What else, right? So speed that you're choosing, and this would be sort of your design speed, right? Or speed limit, or design speed a little bit higher than speed limit, but you get the idea. So that's good. What else? Yeah, friction factor, right? Exactly. So how much acceleration or deceleration can you generate? Friction factor is part of it. Grade can be part of it as well, right? If it's an upgrade, it helps your stopping maneuver. If it's a downgrade, it impedes your stopping maneuver. That means it kind of gives you more acceleration. So you have to neutralize that also. So it's the grade, or basically how much resistance are you able to generate towards stopping movement, right? So it depends on that. What else? Something else, yes. Yeah, so curve radius, yes. So that will be sort of it doesn't, curve or not, it doesn't, like if you slow down. So this is an interesting point. So the response came in, the curve can help you determine the stopping sight distance. Actually, so there is a subtle difference between this idea of sight distance and stopping sight distance. So think about this. Stopping sight distance is what you need, okay? So that typically does not depend on whether you're driving on a curve. Like, if you slow down, then obviously you need smaller sight distance, right? So whether or not it directly doesn't impact your stopping sight distance, right? So stopping sight distance, but it does affect your sight distance, how far you can see. So I hope you can get the somewhat subtle difference between sight distance and stopping sight distance. Sight distance is what's there. What can you see? So curve obviously does impact sight distance. But if you think about stopping sight distance, I'm talking about how much distance you need to stop, regardless of what else might be going on the road, right? So that's your speed, and that's your how much friction you're able to generate, right? What else? One more thing. I need one more thing that affects your stopping sight distance. How much distance you need to stop. Yes. Yeah, so basically the reaction time is one thing I heard, and then your vehicle, what type of vehicle are you trying to stop? If it's a semi-truck, it might require a longer sight distance, and then part of that could be, how much deceleration are you able to generate at that load level and things like that. Yeah, so those are all, good answers. Reaction time is a very important one. And then, what type of vehicle you got going on, that may affect also the stopping sight distance. Now, we'll talk about stopping sight distance for the most part in this class, but I just want to mention here, before we move forward, is that stopping sight distance is not the only maneuver, or stopping is not the only maneuver we worry about. Sometimes you have to allow drivers to be able to see even longer distances. And one of those examples could be what we call the passing sight distance. Again, we are not going to talk about that in this class. Passing sight distance, very important on two-lane roadways, right? So you can see on two-lane roadways, when you have a straight segment, maybe if you're driving to the valley, Central Valley of California from the coast, you do encounter these two-lane roads. And on those two-lane roads, what happens is that sometimes you will see that there is a solid yellow line separating the two directions of travel on the two-lane road. That means usually they provide those solid yellow lines because there is not enough passing sight distance available, right? And sometimes they allow you to pass onto the other side. That means they have deemed that section has enough distance available for you to see what's oncoming, go onto the other side, overtake a slow-moving vehicle, and come back to your own side direction of travel, right? So that's your passing sight distance. Again, the calculations required for passing sight distance are somewhat more complicated. Again, we're not going to talk about that in this class, but we do cover that in CE 422 if you're interested, the roadway design class, the tech elective. Okay, but for this class, we're just going to focus on what I've underlined here. That will be your stopping sight distance. Okay, again, hopefully you can always think about the difference between stopping sight distance, what you need, versus just sight distance, what you have, what can you see on the roadway. Okay, and so physical factors of the roadway will impact the sight distance, and then the driver behavior, the vehicle type, the reaction time, the speed you're going, that will all affect the need that you have for how much distance you need to stop. Okay, so let's talk about stop sight distance estimation. So there are two components to the stopping sight distance. One is the brake reaction distance, and that brake reaction distance is based on, if you're driving the speed limit or at the design speed, at that design speed, if you see a hazard on the roadway, you need some time to react to that hazard, right? You don't react immediately, right? So you take some time to react, and at that time, you have not applied the brakes. So that means you're driving at the same speed that you were at. So basically, you're driving the design speed for the first 1.5 to 2.5 seconds by the time you're reacting to the situation. Okay, so that's your brake reaction distance component. And then you realize, okay, you need to stop. So you apply the brakes, and then there is a decelerated motion, right? So you apply a deceleration rate via your brakes. And then once you apply the brakes, the cars start to slow down. And then you have that decelerated motion. And then you're basically estimating how much distance you need to go from the design speed to zero speed. And again, we have equations of the constant deceleration motion or constant acceleration motion that we can apply and figure that out. And then there is obviously effect of upgrades and downgrades. And then on horizontal and vertical curves. So this is what we are going to talk about in this class, is that what are the sight distance considerations that come into play when you're designing horizontal curves and vertical curves. Okay, so we've talked about horizontal curves, we've talked about vertical curves. Now we are specifically talking about the sight distances on those curves. Okay, now in your textbook, what I have is this table that talks about the two, the two components of the distance, right? So you can see at 15 miles an hour design speed, your brake reaction distance is 55.1 feet. Okay. Now I'm going to quickly talk about where this came to be. So where this 55.1 came to be, that comes from, if you do your design speed of 15 miles an hour, right? So if your design speed is 15 miles an hour, you multiply that by a reaction time. Okay, I'm going to just say reaction time T. Okay, you multiply your speed with the reaction time, it should give you 55.1 feet. Okay, if you multiply the 15 miles an hour design speed, you multiply that by reaction time T, you should get 55.1. Right? Now, the catch though is that, what's the catch here in applying this equation? If I divide 55.1 by 15, would I get my reaction time? I won't, right? Because why? Because the units are off. My speed is in miles per hour, and my distances are in feet. All of this is right here, feet. My design speed is mile per hour. Now, if you remember, I gave you a factor that can tell you what's the conversion between feet and mile is, right? So I'll do this. I multiply that by 1.47. And now if you calculate the T value, that's going to be your reaction time. So what is your reaction time? If you can take out your calculators and tell me what the reaction time looks like according to this table. Okay, let's take a minute, calculate the reaction time. So yeah, so the reaction time, if you solve this equation, comes out to be 2.5 seconds, which is a very conservative value, by the way. Most drivers, unless they're drunk, should be able to react to any hazard on the road within 2.5 seconds, right? So that's how, so they use, so these tables that you find in the AASHTO Green Book, which is the highway design manual at the federal level, and then California has its own highway design manual, and which is very similar to the federal manual, by the way. This table is from AASHTO Green Book, but Caltrans uses something very similar. So according to this, the reaction time is 2.5 seconds, which is plenty of reaction time. And then if you use, so you can basically, if you use that reaction time, you can verify any of these values. So if you do 60 miles an hour speed, multiply that by 2.5, multiply that by 1.47, you'll get 220.5. Right? So that's how these tables came to be. Again, you'll almost never have to calculate this, but I want you to be aware of where these tables are coming from. Because again, this is for so this is braking and stopping sight distance only for flat locations. So it doesn't account for upgrade and downgrade. And in this class also, we'll just focus on, where you can apply this table. We'll focus on the scenario where you can apply this table. Okay, this second equation is our third column of this table is braking distance on level terrain. That means if you have 0% grade, how much distance you will travel once the deceleration starts to happen. And for that, the equation that we use is the equation for the accelerated motion, which is v squared, the final speed squared, equal to u squared, the initial speed squared, plus 2 times a times s. You're familiar with that from your physics, right? The final speed square equal to initial speed square plus 2 times a times s. Now, in this example, you're only talking about when the deceleration is happening. Okay? So now what I want you to do is, I want you to think about what acceleration rate are they using? What is the acceleration rate are they assuming that you're getting? Okay? Now, one of these speed values, so you have initial speed and you have the final speed, and they're calculating stopping sight distance, right? So, or the braking distance, right? So that it's all part of calculating the stopping sight distance. So how would you, if I asked you, how do you figure out what acceleration rate are they using to generate this table? What would you do? You will have one of these speeds to be 0, right? Because ultimately you're stopping. So which speed would you estimate to be 0? The final speed, right? So you'll have 0 on the left-hand side, right? U square. What would you input as U square? The design speed, right? That's the speed you were traveling initially. So let's do with the 15 miles an hour. So I'll do 15 squared. Should I just do 15 squared here? No, but the unit have to be adjusted because I want to find my acceleration in feet per second square, and my distances are always in feet, right? So I'll just do, again, 15 times 1.47. Remember, that's my miles per hour to feet per second conversion. So I'll do that. And then I'll do square of that. Right? So I'll do square of that. Right? Plus 2 times A is what I want to find out. Right? And I want to find out S value. What is the S value that I should input here? The distance that's required to stop. Right? So that would be your braking distance at level terrain. So I'll plug in 21.6. Right? And where am I getting 21.6? This is the first row of this table, 21.6 right here. So you can see that at a lower speed, your reaction distance is much larger than your actual stopping distance. Because once you decide that you need to stop at 15 miles an hour, you can stop within 21.6 feet, right? So let's calculate what that A value looks like. What acceleration or deceleration rate are they assuming? So take a minute, use your calculators to find the A value from this equation. It'll be negative, as it should be, right? Because you're decelerating, so your speed is going down over time. And if you have the A value, you can just blurt it out. So I get negative 11.25 feet per second square. So that's the unit here. Right? So that's good. Negative 11.25 per second square. Now, most cars, most trucks, most everybody will be able to generate. This is a very conservative value again, as they try to estimate it. So what they're saying is that every vehicle will be able to generate at least that much deceleration rate on a flat surface. Okay. Now you can use this value to verify any of these numbers. So if you want to verify for 55 miles an hour, you can verify. So this is the acceleration rate that they're using throughout this table. Okay. And then if you add the two components, the brake reaction and the braking distance, you get the calculated stopping side distance. And then you round it up to the next 5 feet, round it up to the next 5 or 10 feet, whichever one is the, like, you round up. So you can see, so 76.7 becomes 80. 111.9 becomes 115 feet. Okay. So they add these two numbers, they get a calculated number, and then they round it up to the next 5 to get the stopping side distance that you need at a given design speed. Okay. So that's pretty easy. And this is the table we are going to be using. And this is the last column that we'll be using. So anytime somebody says, hey, at 40 miles per hour, how much distance do you need to stop? You need at least 305 feet. Now, anytime the design does not allow drivers to see 305 feet, you have a problem, right? At 40 miles an hour design speed. What happens if the drivers cannot do that? If drivers cannot see, let's say you want to design something for 40 miles an hour, but the drivers cannot see 305 feet. What do? You say, okay, the speed is going to be lower now. Okay, I'm going to lower the speed. The design speed on that curve is going to be much lower than whatever your distance is. You're going to lower the design speed. Sometimes we go the other way. Sometimes in problems, you will estimate how much distance the drivers can see, right? So if somebody says, okay, so let's say you design a curve, and we'll learn how to do that. But let's say you design a curve and you figure out, hey, the drivers can only see 492 feet. Okay. So let's say there is a curve here where the drivers can only see 492 feet is visible to drivers, right? So they can only see 492 feet ahead on a certain location because of the geometry of the situation. Okay, I'm asking you, what's the design speed for that curve or for that section of the roadway? It'll be 50 miles an hour, not 55. Even though you're so close to 55, you cannot have a 55 miles per hour design speed on that. So design speed is 50 mph, not 55. Okay, even though you're so close, you always are conservative. You always want to round it, yeah.
For this, does this change the speed limit or does it change those yellow signs?
Yeah, so it should change the speed limit. Yeah, it should change. So if you cannot provide stopping sight distance, it does change the speed limit, right? So in certain cases, in certain curves, they can get away with, like, if they're in the they can so in this situation, if you provide 50 miles an hour, I wouldn't bat an eye. Now, those advisory speed limit more will come into picture if you're right above the limit, right? So if you're close to the limit, so let's say if you were at I don't know, 430 feet or something, that's where you might want to advise the drivers that, hey, lowering their speed might be even helpful, right? So things like that. But yeah, so it should affect the speed limit for sure. And then obviously our speed limits are a little bit lower than the design speed all the time. So if you see, any speed limit, you can be certain that the design speed is actually a little bit higher. I mean, obviously on straight segments, you can be automan, right? You could see as far as the eye can. So if you're going in the valley or driving from, I don't know, Los Angeles to Las Vegas, I mean, yeah, so that's not a constraint there. You can drive as fast as you can. So that's not, so there, obviously the speed limit is much, much, much lower than the design speed, right? So that's always the case. So yeah, speed, and in certain cases, where you have limitations, it'll be even a little bit lower. So yeah, design speed is always a little bit higher than what you will see as speed limit. Okay, so now that we know this table, I think we're ready to kind of do some work on some problems on how do we provide enough sight distance. Now I show you these slides because what I'm showing you here is sight distance on a crest vertical curve. So on a crest vertical curve, it's basically the hill, right? There, the shape of the curve itself will cause some sight obstruction. Here, we assume that the driver's eye height is h1. So that's where the driver's eye is located. And then they're looking at an object of height h2 located on the straight tangent of the curve, right? So this is vertical curve I'm talking about. So roadway is going up like that and then going down like that. And then what they're saying is to be able to accommodate this situation where you have the driver eye height at h1 level and the hazardous object is of h2 height, then you can estimate the curve that will provide the appropriate sight distance using this formula, 2 times S, which is the stopping sight distance for the given design speed. So let's say, this capital S is the stopping sight distance at that given design speed. And then the minus 2 h1 plus h2 whole squared divided by capital A, where capital A is the absolute change in grade, right? So if it's 3% upgrade and 4% downgrade, your capital A is 0.07. So -3 plus +4, right? So basically just you're talking about the difference in the two grades. Now, the situation could be reversed sometimes. So you can estimate your L length that way. So if you want to design a curve, you can estimate the length of the curve that way, where you're trying to, as a driver, you're trying to locate an object that's located beyond the length of the curve. But that may not always be the case. You might run into this scenario where the curve is already very large and you're trying to, as a driver of eye height h1, you're trying to locate a curve h2 on the other side of the curve, other side of the hill, but you're still within the confines of the curve itself. Okay? So under this scenario, your length of the curve can be determined using this formula where the stopping sight distance S that you need is less than or equal to L. Okay, so that's your other formula. Sometimes you have to apply these formulas iteratively. Okay, but here's the good news, right? The good news is we never have to apply these formulas. We never have to worry about these formulas because we have a conservative estimate that we can get from the AASHTO Green Book tables. So I think you want to note this, that the problems you're going to solve in this class, you never need to apply these formulas. I want you to be aware of these. I want you to be aware of what the S stands for. So S stands for, in this formula, the capital S stands for the stopping sight distance at the design speed you are shooting for in your road. Like, let's say for 40 miles an hour, you can go back to the table. Now you might think to yourself, hey, here the roadway is going up and down. Can I go back and apply this formula, like 40 miles an hour? Can I use 305 feet? Yes, you can, because the idea is that on these vertical curves, approximately, give or take, half of your stopping maneuver will be on the upgrade and half of that will be on the downgrade. And those up and down grades will be milder than the original grades that you're trying to connect. So typically on these vertical curves, it's okay to apply the braking or the stopping sight distance that you calculate from this table. Okay. So capital S value in these formulas is the stopping sight distance from the table I just showed you. You can input that for your given design speed. So in the problems, in the exam problems though, you will never need to apply these formulas that you're going to solve in this class. You will not have to apply these formulas because I'm going to give you another process that produces a conservative estimate of the length of the curve that you need. Okay, so now this L is the length of the curve. Capital S is the stopping sight distance for your given design speed. H1 and H2 are H1 is driver's eye height. H2 is the object height. Capital A is the grade, change in grade. Okay, so the easiest way to do that, and then so there are similar formulas that exist for sag vertical curves. Now I want you to think about sag vertical curves before I give you that easy approach. So here are the formulas for sag vertical curve. Okay, but I want you to think about something first. Okay, so let's say I'm going to design the sag vertical curve first. So let's say if this is my roadway, right? So these are the two curves I'm connecting, the vertical curves, and my roadway looks something like this. So my roadway looks something like this. Oops. I want to draw the squiggly line. So I want to draw something like this. So I want to connect these two curves. Oh, kind of hard to do. But anyway, so you're trying to connect this sag vertical curve. Now, if you think about the crest vertical curves, there was that hill that was blocking the view, right? If you think about that from the previous slide. On the crest vertical curve, if you're the driver trying to locate, this hill was blocking your view. Same thing here. The hill was blocking your view. So if you're at any point behind this point, this hill will come into the way of you seeing the object. But now on a sag vertical curve, there is no obstruction like that, right? You don't have any obstruction. Let's say if you're driving on this curve here, you're driving on this curve here, even if you're here, you'll be able to see pretty much everything. So what's the problem? Where does the sight distance come into play here? Yeah. It'll be the nighttime driving actually, right? Because the headlights angles ensure that you can only see at a certain angle of the headlight. And headlights can only illuminate a certain distance ahead of you. Okay. And that's the problem. That's where the formulas are a little bit different. And then, the H is the eye height of the driver. Tangent beta is the angle for the headlight. S is the stopping sight distance. Capital A means the same thing. And then you have two formulas for the length of the curve that you need to design. Okay. For S less than or equal to L, if you're trying to locate the object within the curve, or if you're trying to locate the object beyond the curve, right? So these are the two formulas. Again, I told you, you'll never have to apply these formulas because we have an easy, ready-to-go table that looks something like this. So here now we're going to just learn to use this table right here. So this table is generic that you can apply it for any situation, any kind of capital A value, the change in grade value that maybe you've been looking for. So this is table 7.6 from your textbook, but then it's also from AASHTO 2001. But again, newer versions have the same thing. But what you have is K factors for stopping sight distance in vertical curves. So we talked about capital K factor in one of the previous lectures. If you remember, does anybody remember what the K factor was for vertical curves? Capital K factor. It was the rate of change of grade. So it was the length required to change the grade by 1%, right? If that length was larger, then you had a much smoother curve, right? So capital A value or K value, rate of vertical curvature, we define that. It's not the horizontal curvature, by the way, right? We had another equation for the horizontal curvature. That's a different thing because that was a circular curve. Now we're talking about the parabolic curve, the vertical curves that we designed. The rate of vertical curvature, K value, you remember that, the K value was the length of the curve divided by capital A, and I'm going to put that in percentage value, in percentage. Okay, so if you plug in capital A value for any curve in percentage, you can get the K value. Okay, so I should probably say plug in A as percentage. Okay, so capital A was change in grade. So let's first kind of revise that value, right? So let's see if I have a curve that connects negative 2% grade with plus 3% grade. What is the capital A value here? What is the capital A value? 5%, right? Because the total change in grade you're achieving is 5%, because the absolute value, it's the absolute value of the difference in the grade, capital A will be 5%. That's just an example. So for any curve, you can estimate that A value. Now, if you had length of the curve, length of vertical curve is, let's say 600 feet. Okay. K value would be what? So what would be the K value for such a curve that connects negative 2% grade with positive 3% grade? So your A is 5%. And if the length of a vertical curve is 600 feet, what would you think is the K value for that curve? It's going to be 600 divided by 5. That'll be 120, right? So you are basically using, so if you're using 600 feet to change the grade by 5%, you're using 120 feet to change the grade by just 1%. This is a very important value to be able to estimate, because first it makes us problem solving on sight distance very, very easy, very straightforward. Never have to worry about those complicated formula, because this gives you a conservative value for both sag and crest vertical curve. And this table 7.6 has something very useful here. So if you look at these parts of the table, it gives you the K value that you need for any design speed for any type of curve. And then if you know the change of the grade that you're looking for, you can easily estimate the length of the curve. Okay. So in this example, I showed you the K value is 120, right? Okay. K value is 120. What type of so if I asked you, what would be an appropriate design speed for this curve? So you figured out the K value here is 120. So you just told me that K is 120 for this curve, right? 120 feet, you can say that, change the grade by 1%, you're using 120 feet of length. Now my question to you is, if I want to find what would be an appropriate design speed for this curve, what would be an appropriate design speed for this curve? What would you say? Can you look up that information in this table? You should be able to, right? So tell me, what's the appropriate design speed for this curve? Yeah.
55.
55. Let's examine this, response here. 55 miles per hour, the K value, but which is my critical value, the minimum K value that I need? Is it for 55 miles per hour, I need 114 for crest curve and 115 for sag curve. What type of curve do I have? I have -2 connected with +3. I have sag curve. So I'm looking for a minimum K value of 115, right? I have 120. So I cannot design a curve with 60 miles an hour because that requires a K value for sag vertical curve to be 136. I don't have 136 K value. I only have 120. So hence, the design speed for this sag curve is 50 mph. And then how do I get that? How did I get that? Because I will highlight this right here. This one right here, that's the minimum required value for that sag curve is 115. But you have 120, so you're good. But you cannot do 60 miles an hour. You cannot do 60 miles an hour because that would have required a K value of 136. Okay, so that's how you're going to solve all the side distance vertical curve problems. You're going to look up the minimum K value from the table, and then you're going to find the appropriate design speed. I think that there is one problem there that you can solve in the homework with that. Yes. Good question. Yeah, design speed is 55 miles per hour. I should say 55. Thank you. Yeah, it should be. So yeah, the appropriate design speed for this curve would have been 55 miles per hour, not 50. Okay. Yeah, so I should correct that here. So I'm going to cross this out here. So this should be crossed out right here. This is wrong. So it should be 55 miles an hour, not 50 miles an hour. Somebody's paying attention. That's good. Right. So 55 miles per hour. Okay, questions, comments? So yeah, you always look up the table. So this table will always give you the minimum requirement. You should always have higher value than that in the field. Okay. So whatever you're going to determine based on the physical characteristic of the curve, that's going to be what's in the field. And then the table will always give you the minimum required value or maximum allowable value. In this case, it's the minimum required K value. Okay. Now, one thing you'll notice about this table that in the test, I will only give you this table, and this actually has the stopping side distance from table 7.4 as well. So it's the last column of table 7.4 is also incorporated within this table. Okay, so you are good there. Does that make sense? Right? So this table, so it can also help you. Hey, what's the stopping side distance for 60 miles an hour? Yeah, you can just say, okay, 570 feet. Okay, so that last column of table 7.4 is also here. So it can help you. So if you only had this table, you'll still be able to solve all side distance problems that are going to show up in the test. Okay, so don't go looking for the table 7.4 and then, hey, professor, you didn't give us table 7.4, because whatever you need from table 7.4 is here. Okay. All right. So let's go and look at. So now I want to talk a little bit about the horizontal, curves and the side distance issue there. Okay. So this was vertical curves where the roadway was going up and down. The hill was blocking your view and things like that. And now we're going to talk about horizontal. Now you might think, okay, on horizontal curve, what could happen, right? What could be the problem in horizontal curves? So now, first thing I want to say is what you have to remember is you're looking at it, the top view of the road. You're not looking at the profile view that you were doing in the previous slides that I was talking about, the vertical curves. Now I'm talking about horizontal curve. So this is what it says, side distance on horizontal curve. Side distance on horizontal curves. And this is section 7.2.4 of your textbook. And now this part is the hardest part of this class. I think I have seen, like, I take you guys do 3 tests in the class. This is where most people lose point in module 2, right? So this is sort of, and even if I look at all module, I think the traffic assignment one, and then this problem, These are the two problems that people most lose points on. So this is where you want to pay attention, right? And it's not that difficult per se, right? So it's not something that you cannot grasp. It's just that there is something going on about this because there are two curves involved, and it's easy to get sort of lost in the details. Okay, so let's just pay attention. And in this problem, when you're talking about the sight distance issue on the horizontal curves, so think about driving on a curved section of the roadway, looking at it from the top. As you drive, when you design the curve, when the roadway designer, design the curve will have its starting point and its end point. So PC and PT. Now they show it as P sub C and P sub T. We've always written it as P, capital C, like that. Either way is fine, as long as you remember that this PC represents the start of the curve, point of curvature. This is point of tangency. Okay, so this is the main curve. This is the whole segment of the curve, whole circular curve alignment. Okay, then you have, like, as you're driving on this road, okay, and then this is a two-lane roadway. This is a two-lane roadway, and the solid line represents the highway center line. Okay, so I'm going to say something here. So I want to say something here. The solid line in this curve, middle, is the center line of the roadway. Okay, so if it's a center line, okay, so solid line in the middle is the center line of the roadway. Okay. Then you have, it's a two-lane road. Or so I should say of the two-lane road. One lane going in one direction, the other in the opposite direction. Okay. Then you have a broken line. Sometimes when I show this figure, and I haven't, because it's a figure that's taken from another textbook. But if you look at this figure here, this point, right, this broken line, it's the center line of the critical inside lane. So I want you to make sure that you grasp this idea that this is not the lane marking. This is not the lane marking that's separating the two lanes. Okay, this is the center line of the inside lane. Now, if you recall, I mentioned that to you, is that we worry about the inside lane a little bit more. Why do we worry about the inside lane on a curve a little bit more than the outside lane? You remember that? Why is it the critical lane? It's a tighter curve, right? Because you're inward, so that means your radius is shorter. That means you require more force to be on that curve compared to if you were on the outside lane traveling that way. So if you're inside lane, so remember, this is center line of the inside lane. This is not the lane marking separating the lanes. Okay, so this is a center line of the inside lane. It says that right here, but I've seen students, because it looks like lane marking, people get confused about that. Then we have, so this is the main curve, is from the highway center line, PC and PT. The radius measured is R. So if you measure this radius, right? If you draw this line right here, this is going to be your R, okay? And if you measure this radius, this is also going to be R, right? So if you measure it, so these radii are all R, but then you are measuring another radius to the center line of the inside lane. So there are actually two curves involved. One is the main highway curve that starts at PC, ends at PT. But then you can think of like a critical curve. Critical curve that's most important for us to analyze from a sight distance perspective. Okay. Now think about this curve a little bit. That curve is measured from the highway center line. And I know I had promised I'm going to look up how this RV came to be. I have not done that yet. At some point I'll do it. But RV is the critical inside lane radius. Okay. And then I'm drawing this point here. that's the start of a new, subsection of the curve, right? And why is that subsection important is because this is the first point at which driver that's traveling from this side, as drivers as they're going in this direction, as they travel in this direction, this is the first point at which they can see around the bend, at which they can see what's happening on the other side of the roadway, right? So this is the driver eye, because if they were here, let's just say, right? What is their line of sight as they try to look around the bend? What is their line of sight? Let me draw that out. So their line of sight looks something like this. So if they were here, their line of sight would be something like this, and that will get blocked by this sight obstruction, right? If they were here, it will still get blocked by the sight obstruction. If they were here, they still get blocked by the sight obstruction. Now, once they hit this point, then this line of sight, for the first time, they can locate what's happening around the bend. Okay? So now, what you want to have happen is that this can help you determine, at what point around is the driver able to see around the bend. And then we define this as MS. If you remember MS, the acronym M or the term M that we had used before, it was for the middle ordinate. That capital M by itself, I had shown you a chart where not a chart, but a figure where M was the middle ordinate. But we defined the middle ordinate for the main curve. Now what we're doing is we're defining the middle ordinate required for available side for sight distance, right? So what we're doing here is this MS is the middle ordinate for the sight distance. Okay, middle ordinate for that subsection of the curve that we want to analyze critically. Okay, now what you want to have happen is that as soon as the drivers can see around the bend, at that point, if they see something that they need to stop for, if they apply their brakes, they should be able to stop before they reach this point, or right as they reach this point for the critical scenario. That makes sense, right? So because if they were at any point before that, any point upstream of that, they can't see what's going on. But this is the first time at which what they can see around the bend, and if they see something hazardous, they should have enough distance available for them to be able to stop. Okay. So what happens now is that if you look at the subsection of this curve, the critical subsection that I'm going to now just sort of draw out here. Okay. And I'm going to draw this out. So the critical subsection of the curve is then this one from here to the center. This line, I'm going to just make them all red. So you can see the red triangle, right? And then if I want to draw the curve itself, it's going to be okay. So I'm trying to draw this curve as best as I can. Okay. So this red portion is now the curve that I'm interested in analyzing. So this becomes my circular curve. And I can look at some directions or some equations. So if you recall from the previous slides that we had seen for the whole curve, whole horizontal curves, I'm going to go back way further back a little bit. I know my drawings are still going to be here, but so if you remember this M formula, this was my M value, right? So this M value, M was R times 1 minus cosine delta over 2. That was for the whole curve. But now I'm interested in applying this same equation, M equal to R times 1 minus cosine delta over 2, the same equation on this curve right here. Okay, so my equation looks something like this. I'm going to draw it out. M is equal to, middle ordinate is equal to R times 1 minus cosine delta over 2. Right, this is my equation. 1 minus cosine delta over 2 is M, but I'm not doing it for the whole equation, right? So if I just kind of focus on that red subsection of this curve, right, that's my critical situation, I can say my MS will be equal to R. Should I put R or RV now? I'm trying to analyze that subsection of the curve that I've highlighted in red ink here.
That'd just be RV.
RV, right? So RV times 1 minus cosine. And again, I'm not interested in the whole delta angle of the curve because that delta angle would be starting from here to here. So this delta angle would have been, if I draw this out, I should just go on this. So this delta angle, if I look at the whole formula, my delta angle would be from all the way from here to here. That would have been my delta in this formula. But I'm not interested in that whole curve. I'm interested in that small portion of this curve, right? So that angle will be delta S over 2. That makes sense? 1 minus cosine delta S divided by 2. Right? So I know it's kind of weird, but okay, so delta. So I should probably just say delta S over 2. Okay, so I'm talking about this angle right here. Okay, so that's my delta S. So I'm analyzing this curve, but I'm using the same exact approach. It's the same circular relationship or same circular curve relationship. MS should be equal to RV times 1 minus cosine delta S over 2. Now, if you want to find, and what you want to have happen is that from here to here, the distance you want is the stopping side distance, right? So now, if I asked you, hey, design a curve where 50 miles per hour is my design speed. If I asked you how much MS, how much clearance distance, we call it clearance distance from the inside lane, how much MS do I need for 50 miles per hour design speed? How would you approach this problem? How would you approach the problem if I said, hey, give me how much distance should I clear from the center line of the inside lane? You know, if there is an obstruction within that distance, I can't have 50 miles per hour design speed, or I have to clear out whatever is here, or to take out the building, or if it's a tree, I need to take out that tree. So my question is, how much MS is required to provide a 50 miles per hour design speed? Okay. How would you approach that problem? Yes.
Find the stopping side distance and then set that equal to the length of the curve.
That's exactly what we are going to do. We are going to, for 50 miles per hour, we have a table that gives you, and we are assuming it's a flat, location, and there's no vertical curve here. But let's say, okay, good. So this is what we're going to do. We can figure out the stopping side distance that I need for 50 miles an hour. So 50 miles per hour require. Okay, so that's my main question. I'm going to say, okay, so I'm going to try to solve it now. So MS, so I need SSDs for 50 miles per hour from table 7.6, right? SSD from table for 50 miles per hour. For table 7.6, let's go back, take a look. How much is that? 50 miles an hour. Do I have that information? Right here, right? 425 feet, right? For 50 miles an hour, I need 425 feet to be able to stop. Okay. So the distance I require from table 5.6 is, what's it, 425 feet, right? Right. Now, then you can do that to find MS value. So using this, find delta S. Okay, use this to find delta S. Delta S is the central angle for that smaller subsection of the curve. Right? It's the delta S is what? If you take MS as your curve, its radius is RV. So delta S angle would be arc length SSD divided by RV. Does that make sense? But remember, this is going to give you angle in what units? If you just did stopping side distance, 425 feet divided by RV, okay, that will give you an angle in radians, okay, not in degrees. So just remember that, right? So just, if you just apply stopping side distance divided by RV, then you will get your angle in radian. Now, one information, 50 miles per hour design speed require how much ms? What you're missing is the radius of the curve, okay? So that is also needed. So let's say that the radius was given to you as for a curve with 1200 feet radius. For a curve with 1200 feet radius. So that's what you're asking. 50 miles per hour design speed require how much ms for a curve with 1200 feet radius? Yes.
Is that RV or R?
That's a good question, right? In the problem, unless they specifically say you're talking about the radius measured from critical inside lane or center line of the critical inside lane, somebody says 1200 feet radius curve, right? So that radius is always from the center line of the roadway, okay? That radius is always from the center line of the roadway. So your RV in this example, so SSD is 425 feet, we said that. And RV will be 1200 minus half the lane width. Let's assume a 12 feet lane. So 12 feet radius, 1200 feet radius. And let me just put like given information as 12 feet lane. 12 feet lane. So what should I subtract to get RV from R? Yeah, 6 feet, right? Half the lane width. Okay, so then your answer will be, or for RV value will be 1194. And then once you have the RV value, your delta S will be 425 divided by 1194. But that's going to be in radian. But that's pretty easy to convert into degrees. What do I do to convert that into degrees? Multiply that by what? How do I convert an angle from radian to degrees? What's the conversion factor? Pi over 180, but it's the reciprocal of that because you're going the other way. You're going from radian to degrees. So it's going to be 180 over pi. Right? So your delta S will be that angle. So what you've done now is you figured out what's going to be this central angle of this smaller subsection of the curve. Once you've done that, right? Once you've done that, you can plug in here and solve the equation. So then your answer will be here, 1194 times 1 minus cosine, okay, delta S over 2. And tell me what that delta S is going to be like. Use your calculators and give me the delta S value for this equation or for this situation. What's going to be my delta S value for this?
We're at 20.4.
20.4 feet or 20.4 degrees then, right? So this is going to be in degrees. Okay. So my delta S, according to this, is 20.4 degrees. Right. So I'll just go. Is that delta S over 2 or just delta S?
So,
delta S. Okay, perfect. So yeah, so you're going to be able to apply this formula here. So 1194 times 1 minus cosine 20.4 divided by 2. And that will give you how much distance you need to clear from the center line of the inner lane so that you are able to provide a 50 miles per hour design speed. Okay, so let's see. What is the answer here? Compute that. What's the answer? Does anybody have it?
18.86 feet.
18.86 feet. That's good. So yeah, that sounds about the right answer, 18.86 feet. So from the center line of the inner lane, you need to clear out 18.86 feet so that the drivers can drive at 50 miles per hour, be able to see. Now, intuitively, if I want to design the same curve for 60 miles an hour, what would happen to the MS value? What would happen to the MS value if I want to design this same curve, same 1200 feet radius, same 12 feet lanes, but I want to design it for 60 miles an hour? What would happen? Without calculations, what would happen to the MS value? It'll go up, right? You need to clear more distance because for 60 miles an hour, this stopping sight distance would be larger. Okay, that means to be able, like you'll need more distance, and that would mean that you'll need this obstruction would have to be moved further back. So this obstruction that you have here would have to be moved further back so that enough distance from 60 miles per hour is visible for the drivers around the bend as they approach that curve. Does that make sense? Right? 70 miles per hour, even larger distances need to be cleared. Right? What happens when you cannot clear that much distance? You lower your design speed gets lower. If you cannot clear, for example, in this example, we said you need to clear 18.86 feet from the center line of the roadway. But if you cannot clear that much distance, what happens? Your curve does not have a design speed of 50 miles an hour. So this problem can be asked in multiple ways, right? This problem could be asked from a design speed perspective, or I could say, hey, I'm able to clear 20 feet from the center line of the inside lane. So I might give you this to begin with. I might give you 20 feet is my MS value. Give me what is my appropriate design speed. Right? So you can do it both ways. The problem could be asked both ways. Either you start here and derive the design speed, or like we just did, you start from the design speed, you go the other way and figure out how much you need to clear. Right? And that depends from a design challenge. It depends on what type of an obstruction you're talking about. If it's not a environmentally sensitive or historically important building or something, then you start, okay, I need to provide my design speed and I'm going to just chop out whatever is in my way or take out whatever is in my way. Okay. But if it's an area where you cannot take out the tree or a building or whatever, right? Then you have to figure out, okay, how much lower I need to make my speed. That makes sense? Right? Okay, good. So let's think about a couple of things about these problems, though, that I've seen students make mistake on, is this idea of getting from R to RV. Now, getting from R to RV, the radius measured from the center line of the alignment versus the critical inside lane radius. That will always change depending upon the configuration of the road, lane configuration of the road. So if it's a 4-lane roadway, it'll be a different scenario than versus if it's just a 1-lane highway off-ramp, right? So think about a couple of these scenarios. If you're talking about, if you're talking about a simple 1-lane, 1-lane off-ramp. Okay, so this is the 1-lane off-ramp that you're designing, and this is the center line of that off-ramp lane. So this is a single lane off-ramp or on-ramp. It could be on-ramp too, but single lane ramp, I could say. For a single lane ramp, what is the relationship between R and RV? The radius measured from the center line of the alignment versus the radius measured from the critical lane. So it's the same, right? If there is only 1 lane, there's no question of inside versus outside. So in this scenario, for a single lane ramp, R will be equal to RV. Now let's say you had a much more complicated scenario of a 4-lane roadway. Okay, so let me draw out a 4-lane roadway for you, right? So you have alignment which has 4 lanes. So this is my center line. Okay, so this is the center line of the roadway. right? And then I have, and now this is lane marking, okay? So I have 2 lanes in this direction, 2 lanes in this direction, right? 2 lane going this way, 2 lanes going the other way. And what I want to find out is, what is the relationship between R and RV in this scenario? Now, R will be measured from the center line of the alignment. So this will be my R. Okay. And let's assume 12 feet lanes. 12 feet means 12 feet wide lanes. What's going to be my RV value here? So your R is measured from the center line of the roadway alignment. You're going to subtract this full lane, so minus 12. And then you're going to subtract half of this inside lane's width, minus 6 feet. So in this scenario, RV will be equal to R minus 18 feet. Right? Make sense? R minus 18 feet in this scenario. So you just have to be, and now if there were median, for example, if there was a physical median separating the 2 directions like we have in a lot of freeways, what would happen? So your R will then be measured from the middle of the median. And then you need to know the median width, subtract half the median width, and kind of go from there. Okay, so just be mindful of the fact that this relationship between R and RV is not like always you subtract 6 or you subtract this or you subtract that. You have to account for the lane configuration of that roadway. So always keep that in mind as you're solving these problems. So that's one thing. R and RV have to be kind of related. The other thing is the same idea applies. Be careful about the clearance distance. Where is that measured from? This MS formula, the formula for MS that I just showed you, that measures, the MS formula measures the distance, the clearance distance between the obstruction to the center line of the inside lane. Okay. Now, in some problem, the clearance might be given from the edge of the right of way or edge of the pavement. Right? So just kind of be mindful of that. Like, where are they measuring the given value? Where is that measured from? And then adjust that to make sure that the MS formula that you apply, it's according to the critical inside lane. Yes.
If you were to like shift where you're studying MS at, would it still works even if it's shifted over to the beginning of the curve?
Beginning of the curve, like from PC?
Yeah, like if you went there and you did that same delta S distance, that distance would still work out because it's a semicircular.
Yeah, it's a circular curve. Yeah, it's always a circular curve. Again, yeah. So in that case, though, remember, if you're in any other point on the curve, the obstruction will be located elsewhere, right? So here what I'm showing you is that everything else is clear. It's just that there is an obstruction that exists over here, right? Okay. So you, let's say if you were, this is a good question actually, because let's say you were driving down over here, then your critical obstructions will be located along the curve somewhere else, right? So it's just basically, I'm showing you one scenario to analyze and generate those formulas for us, right? But again, these critical points will always change. And again, you might have to provide appropriate clearance at all points on the curve, right? So this is going to be like, you're finding the most critical point, but you're interested in making sure that there is clearance on every point as you navigate the whole curve. Okay, so let's see what I've got going on. So I've got this. I think we've solved this problem here. Okay, so let's kind of quickly talk about a couple of things. So let me clear out all the drawings. I gave you the design speed, so 60 miles an hour. Okay, so here it says inside edge of the inside lane. It's a 2-lane highway. So we solved this exact problem for 50 miles an hour, not for 60 miles per hour. Now, what I want you to do is, I want to make sure that you are aware of the fact that your book actually does a good thing, for some people at least. But I always teach it this way because it's good for understanding. But if I want to go back to your book here, go back to this book right here and go to my, should probably go here. But go back to this book here on chapter 7. No, we're running out of time here. One thing I want to show. Yeah. So this is something that's good about your book, is that what it does is it provides that MS value directly as a formula. Like we did in 2 steps. We got the we got the central angle delta S first. So it plugs in that delta S formula, which is SSD over RV times 180 over pi. It plugs into that delta formula, delta S over 2 formula. So you could see that if you look at that here, that formula is already accounted for here. So if you look at that equation 719, it already accounts for that. And then why isn't there 180? Because it cancels out with that 2D. If you have a formula for MS equal to 1 RV times 1 minus cosine 90 into SSD over pi times RV. Okay, so you can directly apply that formula. And remember, I said that this is where you're looking for MS value, right? You're looking for MS value. Now, sometimes, as I said, you might be starting off, from this idea of where you need the design speed. Okay, so then they flip that formula to solve this exact equation for SSD. And it will also kind of cosine inverse, right? It's the same equation. You can directly use it if you wanted to. So always, just remember that you can directly apply these formulas, but you don't always have to do that, right? So as long as you understand how this is coming from, I just want to make sure that you understand that 719 and 720 could be directly applied to solve the problem. This will be the problem we solved, and the problem is on the slide. You can directly apply 719, right? So SSD will come from the 60 miles per hour design speed. Everything else will come from the RV will come from the geometry, and then you could solve for MS to that, right? But then if I gave you that 19 feet of clearance or whatever, right? Then you can solve for SSD first, and then SSD you can go back to the table to find the design speed. Okay, and this is just a rewriting of this formula in terms of cosine inverse solving for this SSD. Everybody clear on that? Right? So again, you can directly have some formulas if you want to write those down. I just always want to make sure that you understand the physical situation, but then if you want to just apply the formula, that's fine as well. So I think your homework problem should be helpful. Okay, so let's go back and take a look at. Let's see where am I? Yeah, so this is basically the chapter 7 issues that I want to talk about. Any questions, comments? And then there are, I talked about how there are other situations like passing sight distance and stuff. So yeah, so you might have to think about that in CE 422. We're not going to cover that. Pavement widening on horizontal curves, because the larger tractor trailers sometimes have trouble navigating, and their tail will sometimes go into the other lane. So sometimes we have to provide wider lanes on those situations. So we just make sure that this happens. Again, we don't talk about that in 321. We talk about that in 422 rather. And then super elevation transition, right? The cross-section design. We haven't talked about that at all. We just mentioned how much super elevation we need for certain curves, right? But to go from that crown section, the basic crown section, to a super elevated section where the outer edge is raised on the horizontal curve, you have to provide that transition. Okay. So yeah, that's basically the discussion I wanted to have on the horizontal curve. Again, these other issues, there will be no problems or questions on that. Just need to be aware of these. And one last thing I want to do is I'll just